Hello, participants of the refresher course in mathematics organized by Ramanujan College of University of Delhi. I am K.S. Charak, Professor at Department of Mathematics, University of Jammu. So, I will be talking about a very fundamental theorem of mathematics, famously known as the fundamental theorem of algebra. As all of you are aware, are familiar with this result, which perhaps you have come across at a high school or a higher secondary school level. And we will be talking about the first proof that we come across during our studentship, somewhere in 11th or 12th class. But certainly the proof is not given there. The only statement is there for us, and we use the statement, we use the result and do many things about the zeros of the polynomials. But here in this lecture, what is our planning? I have to give you the first proof that we come across at our master's level, or maybe at our honors level in different universities as per their course curriculum. So the first proof is by using your complex analysis. Some reasonable stuff of complex analysis is used to prove this theorem. But there has always been an attempt to prove this theorem by the methods which are understandable to a school level student, where we don't use the you can say advanced techniques which are beyond the scope of the students of that level. So here I will be presenting a proof of fundamental theorem of algebra where we use very basic notions of calculus, which are well within the reach of students of 11th or 12th class. So I just start with this basic stuff. This was the theorem about zeros of polynomials. If you look at this bold statement here, this one, every polynomial of degree at least 1 with complex coefficients has a 0 in C. C is the set of complex or the field of complex numbers, we can say. So this is the statement. Basically, this was the result given by a German mathematician called Friedrich Gauss, who is commonly regarded as one of the greatest mathematicians of all times, and he is also known as the Prince of Mathematics. He has contributed to diverse branches of mathematics and physics. But among all his accomplishments, all his achievements, one of the fundamental results that I was talking about, the fundamental theorem of algebra, is the basic one. And the statement is quite simple and easy even for a school student to understand. But how to prove it, that is the major question. So this statement we come across, as I said, at a school level, but certainly with a remark. The statement is given there, but either there is a footnote or there is a running remark that the proof of this fact is beyond the scope of this book. So we don't introduce the proof of this theorem to the school students simply because the tools, the techniques, the procedures used to prove this theorem are really beyond the scope of the students of that level. So what I shall be doing, I shall be presenting first the proof of this fundamental theorem of algebra that we come across, the first proof using the complex analysis. But before I start with that proof, we have to recall some basic things, though I hope, as I am told, that all of you are assistant professors teaching undergraduate classes, and I don't know what are the course curricula, but generally this basic complex analysis is all known to you because you are already masters, or some of you are PhDs, maybe with higher qualifications. But this is the primary course that all of you might have done during your masters, or even at present you must be teaching it at certain level. So I will be simply recalling these basic facts which I will be immediately using it. I will not be using the hardcore complex analysis, but whatever I shall be utilizing in the proof, I will be explaining it side by side. Okay, so let us recall first that this C, as we denote the field of complex numbers, it is nothing but this is the set of ordered pairs of real numbers, which we generally write as z equal to x plus iy. This I is nothing but this is the imaginary unit satisfying I square equal to minus 1. It is a field, as I said, and it is not an ordered field. So you can check, or you might have checked it during your course of study. And here by domain we shall mean an open connected subset of C. And if complex valued functions on a domain D in C is said to be differentiable at a point z0 in D. If you look at the limit of this, what you call limit of this quotient, limit as z tends to z0, f of z minus f of z0 upon z minus z0. If this limit exists, irrespective of the manner in which z tends to z0. Now we have to be very particular about the limit, because this is not the real limit, this is the complex limit in the complex plane, because z0 is a point that there are not only two ways as we do on real line. There are only two kinds of limits, left hand limit and right handed limit. There are only two ways, left and right approaches towards the point, but here we have arbitrary approaches to approach z0. So this z approaching to z0 means you are working in a small neighborhood of z0. So this z can approach to z0 in any manner along any curve, along any path. But in all the cases, this limit must exist as a unique number. So if this thing happens, then we say that the function is differentiable. And we say that this function is holomorphic at a point z0 if you are able to find out a neighborhood of this point, a small neighborhood of this point z0, at each point of which this function is differentiable. So for a function to be holomorphic at a point, you need to have a neighborhood of that point at each point of which the function is differentiable. So locally these two things are different. Differentiability, analyticity implies differentiability. I means the analyticity means holomorphic, because holomorphic and analytic, these are the synonyms, we can use them interchangeably. So that means holomorphic functions are differentiable functions. But if you look at the global definition of your holomorphic function, that means f is holomorphic in whole of the domain if and only if it is differentiable at each point of D. So then the two concepts are going to be the same. So this is all about this holomorphic, and what we have to do. Holomorphic functions are continuous because they are differentiable, therefore they are continuous. What are the simplest examples of holomorphic functions? The polynomials. And if you look at the algebra of holomorphic functions, that is sum of the holomorphic functions is always holomorphic, product of holomorphic functions is holomorphic, quotient of the holomorphic function is holomorphic provided the denominator is not 0. Yeah, that thing is to be there. So you know that, as I said, polynomials are on C are the simplest examples of holomorphic functions. Polynomials are holomorphic functions on C, and generally the holomorphic functions on C are called entire functions. That means the functions which are holomorphic on whole of C are called entire functions. Therefore, the immediate examples of entire functions are the polynomials again. So that means polynomials are entire functions. They are differentiable everywhere in C. And the entire functions other than polynomials, those functions are known as transcendental entire functions. For example, exponential function, the sine function, sine z, similarly cosine z, are their combinations. These are the simplest examples of your transcendental entire functions. Right. About entire function, there is one famous theorem in complex analysis. You have done it. That is Liouville's theorem. What this theorem says? Liouville's theorem says that every bounded entire function reduces to a constant. You take any bounded function which is entire means on whole of the complex plane, and boundedness means again on whole of the complex plane. So this is bounded entire function on whole of C. If this thing is there, then it must be a constant function. So precisely every bounded entire function reduces to a constant. So this is the basic stuff right now which we should have at hand to proceed to have the first proof of your fundamental theorem of algebra, which we usually do at master's level or maybe at honors level in certain universities, certain institutes. Okay, so I go to this proof of fundamental theorem of algebra. So we have to be particular about these polynomials. So generally the polynomials of degree n greater than or equal to 1 is given by this expression. It is pz equal to an zn plus an minus 1 zn minus 1 a naught an. An is not equal to 0, that means that says that this is a polynomial of degree n. But remember that we are considering non-constant polynomials, that means the degree has to be greater than or equal to 1, because 0 degree polynomials are the constant functions. That's why we put this an not equal to 0. It has to be of degree n. Now I have to find out a certain estimate, and this is the easiest estimate. If you look at the modulus of this function, so then I can immediately, just taking an zn out of this expression, so it will be nothing but this will come out as 1 plus, if I take this term out, it will be remaining term inside will be 1 plus an minus 1 upon an z plus so on a naught upon an zn. So this thing will be like this. So I take the modulus on both the sides, then this will be coming out as modulus of an mod z to power n, and so I have this thing inside. But remember that by triangle inequality, if I take this modulus inside, then certainly this thing will be greater than or equal to 1 minus mod of this plus mod of this plus 1 mod of this. Or this I can further break into mod of an minus an into 1 upon mod z, so on, modulus of this into 1 upon mod z to power n. That means mod z is in the denominator here. Okay, so if I look at this bracketed expression, then if I take mod z arbitrarily large, that means if mod z is tending to infinity, so this term will become 0, this term will also become 0, and this whole thing will tend to 1, because this portion will become 0 as mod z tends to infinity, this will become 1. So that means the entire thing of the limit will depend on this. Mod an is not equal to 0. So the whole thing depends on this. If mod z is tending to infinity, that means this term is also tending to infinity. So that's why I say that this whole expression tends to infinity as mod z tends to infinity. So that means modulus of pz, when p is a polynomial of degree n greater than or equal to 1, then this polynomial has the modulus which is tending to infinity as mod z tending to infinity. So what does it mean? That means when mod z is arbitrarily large, then modulus of pz is also arbitrarily large, or it tends to infinity. So that is, there is an r greater than 0 such that this thing tends to infinity for all z such that mod z is bigger than r. That means mod z is arbitrarily large, or in other words mod z tends to infinity. So this is important thing, so you have to note it. This is going to be your first you can say conclusion about the polynomials, growth of the polynomials. So whenever mod z tends to infinity, modulus of pz tends to infinity. Remember this thing. So this is the simplest estimate from this polynomial of degree n. Now we start with the proof. We suppose on the contrary, we have to prove that this polynomial has a 0 in C. We suppose on the contrary. We shall use the method of reductio ad absurdum. Suppose fz has no 0 in C, fz is not equal to 0 in C, then certainly the quotient of two holomorphic functions is going to be holomorphic. Therefore, 1 upon pz is holomorphic in C. Constant function is holomorphic, pz is holomorphic, and pz is not equal to 0. Therefore, this quotient is holomorphic in C. Holomorphic in C means this is entire function. So that means this 1 upon pz is an entire function. And if this is an entire function, then I can use this inequality. Mod pz is tending to infinity. 1 upon mod pz will tend to 0. As simple as we can handle it. By first, for any epsilon bigger than 0, we have, see, this thing is tending to 0. That means this thing is arbitrarily small for arbitrary large mod z. That means mod z tending greater than r. So this expression is going to be arbitrarily small outside a circle of radius r. Remember, you draw a circle of radius r, mod of 1 upon pz is going to be very small outside that circle. So what happens on the circle and inside of that? That part is still to be handled. Now consider the disk, closed disk of radius r with center at 0. This is the disk. Remember that this is a closed disk. So this is closed and bounded set, and so it is compact. You know that this is entire function. That means it is holomorphic on whole of C. So it is differentiable and hence it is continuous. Therefore this thing is going to be continuous. And this is a compact set. So continuous functions on compact set, they are bounded. So that means on this set, that means inside the circle as well as on this boundary, this thing is going to be less than or equal to m. So for this entire function 1 upon pz, its modulus has two kinds of behavior. Outside the circle, it is going to be less than epsilon, and on the circle and inside the circle, this is going to be less than or equal to m. So that means if I pick up the maximum of these two, epsilon and m, if I consider m naught to be the bigger one of the two, then modulus of 1 upon pz will be less than or equal to m naught anywhere on C. That means this m naught is maximum of epsilon and m. Therefore, this bound is true, or this bound is valid for every z in C, outside the circle, on the circle, and inside the circle. So therefore, modulus of 1 upon pz is less than or equal to m naught for all z in C. That means this entire function 1 upon pz is bounded on C. This is entire. This is bounded on C. So you have seen in this Liouville's theorem, this is Liouville's theorem, every bounded entire function reduces to a constant. So therefore what happens? Therefore, this 1 upon pz reduces to a constant by Liouville's theorem. And if 1 upon pz is constant, then certainly pz is constant. Pz is constant means it is a polynomial of degree 0, which is not true. Why? This is a contradiction. Why? Because our polynomial is not a 0 polynomial. It is not a constant polynomial. It is not a 0 degree polynomial. It is a polynomial of degree n greater than or equal to 1. So this is also the simplest proof one can understand. But the question is, Liouville's theorem involves a lot of complex analysis, because you perhaps you can recall that during your master's degree or in whatever at whatever level you come across this Liouville's theorem, you have to use a lot of complex analysis to prove this theorem. And if this kind of proof is presented before the school level students, I mean 11th or 12th class students, it will be very difficult for them to understand, because to understand this proof they need to have some basic course on complex analysis, which is not recommended at that level, right? So therefore we must have a proof of fundamental theorem of algebra which is understandable to the students of school level, right? So that is basically the purpose of this lecture, purpose of selecting this fundamental theorem of algebra. And next I will be giving you the simplest proof where only calculus is used and simply the definitions or the very basic elementary knowledge of complex numbers is used to achieve that proof, right? So next thing we shall do, we shall present that proof, right? So and this is the proof actually. See, this is not my proof basically. This is a proof by three mathematicians of University of California, Davis. They proved it in 2007. Basically, these are their class notes, but it is a copyrighted thing, so we need to give the reference of this. So these are the mathematicians: I. Lancome, B. Nastrelli, and A. Schilling of University of California, Davis, 2007. And they have proved this. So this proof is due to them. So I have simply explained and given you the details about this, because this is very interesting and very beautiful proof for school level students. Very simple, involving only basic calculus. So the first thing that we need to have in this direction, you consider this closed disk in R2. R2 is basically the complex plane. This is simply the way that we want to involve these two real variables. So closed disk is nothing but set of all those ordered pairs here, such that x1 square plus x2 square is less than or equal to r square. So that means this thing is nothing but it is a closed disk with center 0 and radius r. Now on this disk you define a real valued function f, and suppose it is continuous on the open disk, and f is bounded. Then f is bounded because it is continuous and this is a compact set, so it has to be bounded. It is continuous, and therefore it attains its minimum as well as maximum on this compact set, on this closed and bounded disk. Once it attains its minimum and maximum on this disk, then I must be able to find out 2 points in this closed disk, xm and xm, such that this stands as the minimum value and this stands as the maximum value of this function. You know that all the values of each point in the disk are lying between fxm and f of x capital M. So that means these are the extreme values, fxm and fxm, these are extreme values. So that means extreme value theorem says that the extreme values are attained by a continuous function on the closed disk with center 0 and radius r. So this is the extreme value theorem. Calculus part is this one, that extreme value theorem is to be used here. We will not be using the Liouville's theorem or any kind of advanced conditions. But I just stop here, and this proof and the further details will be taken up in our next lecture. So just wait till the next lecture. Thank you very much.